James Webb was built to look deeper into space than any telescope before it. What it found was not just beautiful, it was unsettling. Galaxies appearing far too early, black holes growing too fast, and distant worlds with atmospheres that raise questions science still cannot fully answer. The deeper Webb looked, the more the universe seemed to break the timeline we thought we understood. If that kind of mystery fascinates, please take a moment to like this video, subscribe to the channel, and share it with someone who loves space and cosmic discoveries. It truly helps the channel grow, and thank you for being here and spending this time with us. And before we begin, it would be lovely to know what time is it where this is playing, and where in the world is it being heard from tonight. Now, settle in and let's begin. For years, the early universe exists in astronomy as a dim outline, a place inferred more often than seen, described with confidence only because there is so little detail to contradict the story. The first stars are expected to appear slowly out of cooling hydrogen and helium. The first galaxies are expected to be small, irregular, and unfinished, more like rough drafts than settled structures. Even the language around them carries caution. Estimates, candidates, possible detections, tentative fits. Then James Webb begins to look, and almost immediately the uncertainty starts to thin. It does not vanish, because the universe rarely offers anything so clean, but the old haze is replaced by something far more difficult to ignore. The telescope does not simply see farther, it sees with a kind of calm precision that turns distance into evidence. That is why the first deep image matters so much. At a glance, it appears almost harmless. A dense field of points and smudges spread across black space. Another beautiful astronomy image waiting to be admired and moved past. But the longer it is examined, the less decorative it feels. The field is centered on SMAC 0723, a massive galaxy cluster in the constellation Volans, sitting roughly 4.5 billion light-years from Earth. By itself, that is already an enormous distance. Yet the true power of the image lies not in the cluster alone, but in what the cluster does to everything behind it. Its mass bends space. Light from more distant galaxies is stretched, curved, magnified, and pulled into arcs around the foreground cluster. This is gravitational lensing, a consequence of general relativity, but in practice it behaves like something stranger. It acts as a natural distortion field that does not hide the background universe so much as expose it in fragments. A galaxy too faint to notice becomes visible because its light is twisted and amplified on the way here. A smear of infrared light becomes a message that has crossed more than 13 billion years to arrive. In that first image, Webb is not merely looking into distance, it is looking into time, into an era when the universe is still very young, only a few 100 million years removed from the Big Bang. According to the standard picture, this is a time when structure is just beginning to assemble itself out of darkness. Matter is still falling together. Stars are only beginning to ignite in great numbers. Galaxies should be primitive and unstable. And yet some of the objects in that field refuse to behave like early drafts. They're too bright, too compact, too coherent. Their light suggests dense populations of stars, vigorous formation, and in some cases a degree of organization that should require more time than the universe has apparently allowed. It is not that Webb sees one impossible thing and throws cosmology into crisis on the first day. It is subtler than that, and therefore more unsettling. It sees several things that seem slightly too advanced, slightly too luminous, slightly too developed, and those slight deviations begin to accumulate. That is often how real scientific discomfort begins, not with a single impossible observation, but with a pattern of facts that lean in the wrong direction. What makes this first moment especially disturbing is how quickly it arrives. The image is not the result of years of dedicated deep surveying. It is an early demonstration, almost an announcement that the telescope is finally awake and working. Yet even in that first demonstration, the data refuses to sit quietly inside established expectations. In the past, a suspicious object at extreme distance can often be explained away by poor resolution, contaminated signals, or inadequate sensitivity. A fuzzy point of light can be many things when seen badly. Webb changes that. Its mirror, its infrared instruments, and its location far from Earth's warmth give it a clarity that earlier observatories cannot easily match. Hubble can reach extraordinary distances, but Webb is built to see the stretched infrared light of the early universe more directly. Light that has spent billions of years travelling through expanding space until once visible wavelengths are pulled deep into red. What was once hidden becomes available. What was once guessed at begins to show shape. That is the transition that makes the first image feel less like a triumphal postcard and more like the opening of a case file. Once the arcs are measured, once the redshifts are estimated, once the faintest objects are sorted from the foreground clutter, the early cosmos begins to look crowded, not with a few weak islands of light barely struggling into existence, but with thousands of galaxies in a tiny patch of sky, each a system of stars, dust, gravity, and history. The mind resists that scale at first. A region of sky no larger than a grain of sand held at arm's length contains more galaxies than ordinary intuition can hold. The darkness is not empty, it is only distant. And when distance is reduced by lensing and infrared sensitivity, what emerges is not a gentle beginning but something more abrupt, more active, more mature than expected. That is where the unease deepens. If galaxies in the very early universe already possess enough stars to shine so strongly, then those stars must have formed with startling efficiency. If those stars have already lived and died in part, then some chemical enrichment may already be underway. Heavy elements do not appear for free. They are forged in stars and scattered by violent ends. Dust does not simply exist from the start. It is made. Structure does not arrive by declaration. It has to build. Every bright early galaxy therefore carries a hidden demand. It asks how the universe moved so fast. Did the first gas clouds collapse more readily than expected? Did dark matter shepherd matter into place with greater speed? Did the first generations of stars burn hotter, faster, and in greater numbers than the old models preferred? Or is something more basic at issue? Perhaps the timelines derived from limited earlier data were too gentle, too linear, too tidy. The standard picture is not abandoned, but it suddenly looks incomplete, as if it has been describing the early universe from too far away to notice its true pace. Webb does not offer an answer in that first image. It offers a tension. The data is good enough to narrow the excuses, but not yet complete enough to settle the matter. That is exactly the kind of tension that drives astronomy into its most interesting territory. There is also something psychologically strange about the way this happens. For decades, the deep past is treated almost like sacred territory, remote and abstract, reachable only through indirect measurement. Then a single image arrives, and the deep past begins to look populated, textured, and specific. The old distance remains, but the emotional distance collapses. Ancient galaxies are no longer anonymous theory. They are visible systems with shapes and brightness profiles, with warped echoes wrapped around a foreground cluster like fragments of a broken code. Beauty remains, but it is no longer the main point. The image becomes troubling because it is so convincing. It does not appear mysterious in the usual sense, with shadows hiding the truth. It appears mysterious because it is too sharp. It shows enough to make the old story feel exposed, but not enough to replace it with a new one. That leaves astronomy in an uncomfortable position. The telescope built to confirm the broad outline of cosmic history instead begins its work by sharpening the very details that make that history harder to explain. A field once thought empty turns out to be crowded. A young universe expected to be tentative turns out to be busy. A first image intended to inspire quickly becomes evidence that the dark, when finally examined, is not quiet at all. It is already full of light, already full of structure, and perhaps already moving according to a tempo that no one fully anticipated. After that first unsettling look into the deep past, the telescope turns toward a different kind of darkness, one much closer, and somehow just as difficult to interpret. These are not ancient galaxies balanced on the edge of the visible universe, but planets circling other stars, worlds that have existed for years in astronomy as shadows, dips in brightness, slight wobbles in starlight, mathematical traces that imply a presence without revealing much about the thing itself. For a long time, that is enough. It allows astronomers to count planets, estimate size, infer mass, guess at temperature, and sort them into broad categories. But even the most successful methods still leave those planets strangely unreal. A world discovered by transit, when it passes in front of its star, is known mostly by the small amount of light it blocks. A world found through stellar motion is known by how strongly it tugs. In both cases, the planet feels more like an effect than a place. James Webb begins to change that. Its infrared instruments do not simply confirm that these planets exist, they begin to taste their atmospheres. When starlight passes through the thin outer layers of a planet's sky during a transit, certain wavelengths are absorbed by gases present there. That missing light forms a pattern, and if the telescope is sensitive enough, the pattern becomes chemistry. The principle is straightforward. The consequence is profound. For the first time, distant worlds stop being defined only by orbit and silhouette. They begin to reveal what is actually hanging in their air. One of the earliest and clearest examples comes from WASP 39b, a hot gas giant orbiting a star roughly 700 light-years away. No one mistakes it for a place where life is likely to thrive. It is swollen, scorched, and intensely irradiated, more laboratory than oasis. Yet it becomes one of the most important planets Webb studies precisely because it is so atmospheric, so easy to read compared with smaller and quieter worlds. The telescope detects carbon dioxide in its atmosphere with unusual clarity. That matters not because carbon dioxide is rare in itself, but because the detection proves that Webb can do the work it was built for. It can separate starlight into fine spectral bands and recover the fingerprints of molecules from a planet that cannot be seen as a disk and cannot be visited. A world so distant that all knowledge of it depends on a thin subtraction of light from light. Suddenly the method is no longer theoretical promise. It functions. And once it functions on one planet, the interpretive space opens quickly. If carbon dioxide can be seen, then water vapor can be sought with more confidence. Methane becomes a target. Sulfur compounds become relevant. Cloud layers, temperature gradients, hazes, and circulation patterns stop being fantasies attached to artist impressions and become physical questions attached to data. That is when the tone of discovery begins to shift from achievement to strangeness. Webb examines WASP 18b, a massive and blistering world pressed close to its star, and sees water vapor, where extreme conditions still allow chemistry to be measured. It studies WASP 80b and finds a combination of molecules that helps refine ideas about cloud cover and heat transport. It looks at GJ 486b, a rocky planet much smaller than the gas giants that dominate early atmospheric work. And the observations stir a more delicate question. Is the signal coming from the star, whose active surface can complicate everything, or from the planet itself, perhaps from a thin atmosphere heated beyond anything familiar? Even when certainty remains out of reach, the important change has already occurred. Webb is forcing astronomy into a new discipline of planetary reading, where the problem is no longer merely whether a planet exists, but how to disentangle the physical story of its sky from a narrow thread of infrared data. That might sound like a technical refinement, but it carries a deeper implication. The more clearly those atmospheres come into view, the less they resemble simplified versions of planets in the solar system. They are not merely hotter Jupiters or larger Earths. They are their own kinds of worlds, with chemistries and weather systems that seem to have developed under rules that are familiar only at the level of physics, not at the level of experience. WASP 17b makes that point in a particularly unsettling way. This planet is a bloated giant with a low density and a feverishly hot atmosphere. Webb detects signs of tiny silicate particles in its upper air, essentially mineral grains, glass-like material suspended high in the atmospheric layers. On Earth, clouds are made of water droplets or ice crystals. Even in the harsher climates of the solar system, clouds are still understandable in relation to local chemistry and temperature. But on WASP 17b, the sky appears capable of carrying particles that would on Earth be associated with stone and melting. It suggests a climate where the idea of weather detaches from ordinary intuition. There may be drifting mineral haze, glassy aerosols, perhaps even precipitation made of materials that belong in furnaces rather than clouds. This is not merely exotic for the sake of spectacle. It reveals a deeper lesson. Planetary atmospheres are not variations on one theme. They are expressions of whatever conditions happen to prevail: pressure, radiation, gravity, composition, circulation, chemistry, all interacting without any requirement to resemble home. Webb is not finding strange weather because it is looking for the dramatic. It is finding strange weather because the universe never promised familiarity. Once that lesson settles in, every atmospheric spectrum begins to feel like a partial glimpse into an alien logic. Sulfur dioxide on one world suggests photochemistry driven by intense starlight. Methane on another speaks to different temperature regimes and chemical balance. Water vapor may mean humidity in the broadest possible sense, but it does not imply oceans, rain, or habitability. Even the word atmosphere becomes slippery, because on some of these planets the air may be so hot, deep, compressed, or irradiated that the boundary between sky and furnace grows thin. What Webb supplies is not reassurance. It supplies evidence that planetary diversity is far greater than the old catalogues could comfortably express. The telescope does not show one road toward Earth. It shows a crowd of roads leading elsewhere. That crowd matters for another reason. Astronomy has long hoped that by building from gas giants to smaller rocky planets, instrument by instrument, it will eventually reach a point where biosignatures on an Earth-sized world can be assessed with real discipline rather than hopeful speculation. Webb does not complete that journey, but it changes its starting point. Before, the search for life beyond the solar system often rested on distant optimism and broad population statistics. If planets are common and temperate zones exist, then perhaps some fraction host biology. Now the search begins to acquire texture. It becomes clear that atmospheres can be measured, but also that interpretation will be treacherous. Carbon dioxide is detectable, but common. Methane is enticing, but not decisive. Water vapor is exciting, but context-dependent. The same molecule can mean abundance, desolation, photochemical breakdown, volcanic release, or something not yet imagined. A single spectral line can invite a headline and still remain deeply ambiguous. That ambiguity is not a weakness in the data, it is a property of nature itself. Webb reveals that the chemistry of distant worlds will not hand over simple answers. It will offer combinations, tensions, partial patterns, and clues whose meaning changes depending on what surrounds them. And beneath all of this sits a quieter disturbance. The telescope that was expected to open a new age of planetary clarity also begins to expose how narrow earlier expectations have been. Exoplanets were once grouped into a few tidy categories because that was all the data could support. Hot Jupiter, super-Earth, mini Neptune, gas giant, rocky planet. Those labels still help, but Webb starts to make them feel provisional, as if each category is only a drawer filled with objects that happen to share size, while concealing entirely different internal histories and atmospheric behaviours. One planet carries vaporized minerals, another shows sulfur chemistry shaped by fierce radiation, another hints at atmospheric survival on a scorched rocky surface. The more detail arrives, the less the planets sit still inside their labels. It becomes possible that the galaxy is full not merely of many worlds, but of many kinds of worlds, some with skies so unlike anything in the solar system that language itself must keep adapting to describe them. That is why the exoplanet work feels more consequential than a technical milestone. It is not simply that Webb can read alien atmospheres. It is that once those atmospheres begin to speak, they do not say what anyone would have said for them in advance. They are richer, harsher, stranger, and less obedient to analogy than expected. Every successful observation brings another layer of reality into focus, and with each layer comes a subtle erosion of certainty. A planet is no longer a point on a chart. It is a place with heat, motion, chemistry, and hidden structure. But the closer it comes into scientific view, the further it seems from easy comprehension. In that sense, the telescope repeats the pattern established by its first deep image. It brings clarity, and the clarity does not comfort. It removes the blur, and what remains is not simplicity, but a sharper mystery. Then the telescope turns inward, and something unexpected happens. The sense of distance does not disappear. It changes scale. After ancient galaxies and exoplanet atmospheres, the solar system should feel familiar, almost domestic by comparison, a place already charted by probes, mapped by long campaigns, named and sorted into categories that seem stable. Neptune is a cold giant. Europa is an icy moon. Comets are dirty remnants from the solar system's formation. Trans-Neptunian objects are frozen leftovers in the deep outer dark. Asteroids are rocky fragments, interesting mostly when they cross near Earth or preserve an old composition. That is the comfortable version. It is not wrong, but it is incomplete in a way that only becomes obvious once Webb applies the same patience and infrared sensitivity to objects much closer to home. The telescope begins to look at worlds and bodies that should, in theory, surprise less than primeval galaxies. Instead, it shows, again and again, that familiarity is often just a result of having looked with insufficient detail. Neptune is one of the first reminders. The planet has been seen many times before, including by Voyager and Hubble, and it is not hidden in any absolute sense. Yet Webb's view carries a different kind of definition. The rings come through with unexpected crispness, no longer faint suggestions but delicate structures sharply outlined against the dark. The atmosphere reveals high clouds and a brightness pattern near the poles that hints at thermal behaviour and circulation, more complex than a casual glance would suggest. Neptune has always been a difficult planet to think about properly because it is both large and remote, visually grand yet scientifically elusive. It sits so far from the sun that ordinary intuition about weather begins to fail, yet it is not dead or static. Winds there can reach astonishing speeds. Methane shapes the colour seen in visible light. Seasonal changes unfold across spans that make human observation feel like the blink of an eye. Webb does not suddenly solve Neptune. It does something more unsettling. It makes the planet look active in a way that reminds astronomy how much remains hidden, even on worlds already known by name for centuries. The giant at the edge of the classical planets is not merely a distant blue sphere. It is a system still moving, still shifting, still only partly understood. That pattern deepens when the telescope observes Chariklo, a much smaller and stranger object orbiting between Saturn and Uranus. It is classified as a centaur, one of those bodies that seem caught between categories, not quite asteroid, not quite comet, inhabiting a region of instability and transition. Chariklo is already unusual because it has rings, a feature once thought almost exclusive to giant planets. Rings around a body so small feel almost improper, as though some unwritten boundary has been crossed. Webb studies it and detects water ice, helping to sharpen the sense that even minor bodies can preserve complex surface histories and dynamic environments. A ring system around an object only a few hundred kilometers across suggests delicacy and persistence existing together. Fine structure wrapped around something too small to dominate its surroundings, and yet somehow capable of holding on to that structure anyway. The solar system, seen this way, no longer looks like a clean hierarchy with major planets at the center of interest and lesser debris scattered in supporting roles. Small bodies start to resemble archives. They hold on to conditions from early formation, collisions, migrations, freezing, sublimation, and radiation. Their surfaces are not blank. Their compositions are not trivial. They carry memory. Europa carries a different kind of memory, one hidden beneath ice. For decades it has stood near the center of astrobiological imagination, because earlier missions and observations suggest an ocean below its frozen crust. The logic is compelling. Tidal flexing from Jupiter's gravity can heat the moon's interior. A deep ocean may remain liquid under the shell, where there is liquid water, energy, and chemistry. The possibility of life can never be entirely dismissed. Yet possibility is not enough. It hovers too easily in the realm of attractive story. Webb adds something firmer. It detects water vapor associated with plumes venting from Europa into space, reinforcing the idea that the moon is not sealed shut but geologically active, capable of releasing material from below or near below the surface. The importance of that lies in access. An ocean buried under kilometers of ice is scientifically tantalizing and practically distant. A plume is different. A plume is leakage. It is the hidden interior speaking in bursts. It means that the moon may occasionally offer up samples of its concealed environment without requiring a machine to drill through the crust. Even if the source regions of the vapor remain debated, the broader impression becomes difficult to ignore. Europa is not a frozen relic. It is restless. It exchanges matter with space. It may be cycling energy and chemistry through an unseen sea. What had long been suspected begins to feel more immediate, and with immediacy comes a sharper kind of mystery. If a moon in the outer solar system is venting water into space today, then the ancient question of habitability is no longer purely historical. It becomes present tense. Comets, too, begin to resist their usual simplicity. They are often described as time capsules from the early solar system, primitive leftovers preserving original material from the era of planet formation. That description contains truth, but it can also flatten them into symbols rather than bodies with distinct histories. Webb's observation of Comet 238P Reid illustrates the problem. The telescope detects water, but not carbon dioxide in the proportion many astronomers might expect. That absence is not merely a missing ingredient on a checklist. It points toward formation conditions and thermal history. If carbon dioxide is scarce or absent, perhaps the comet formed in a warmer region than assumed, where more volatile compounds could not remain trapped as easily. Or perhaps it once contained them, and has since lost them through repeated passages and slow processing over time. Either way, the object ceases to be a generic comet and becomes a specific chemical puzzle. If comets differ in their inventories more than simple models suggest, then using them to reconstruct the early solar system becomes both more difficult and more interesting. They're not interchangeable messengers from the past. They are individual witnesses, each altered by where it formed, how it moved, and what it endured. Out beyond Neptune, the trans-Neptunian objects add another layer to this inward turn toward the unknown. These bodies inhabit the cold borderlands of the solar system, regions so distant that sunlight is weak. Temperatures are severe, and change is often assumed to be minimal. Yet Webb detects signs of methanol and organic compounds on some of them, reinforcing the idea that the outer system is chemically rich, not chemically exhausted. Organic molecules in this context do not mean life. They mean carbon-bearing compounds, ingredients and intermediates that matter because they reveal how chemistry unfolds in frigid environments over immense spans of time. Radiation can alter surfaces, ice can preserve ancient states, collisions can expose buried material. Migration in the early solar system may have mixed populations formed in different places. The farther out the telescope looks, the less those distant bodies appear as uniform frozen debris. They become records of chemical evolution in slow motion, shaped by isolation but not exempt from transformation. Even small near-Earth objects begin to matter differently under Webb's gaze. A dark asteroid crossing the inner solar system might once seem beneath the notice of a great space observatory built to study the earliest galaxies. But small bodies are difficult precisely because they are faint, fast, and often compositionally obscure. Observing them well refines more than orbit calculations. It sharpens understanding of surface materials, thermal behavior, and the physics of how such bodies absorb and re-radiate sunlight. It helps determine whether a tumbling object is rocky, metallic, or rubble-like, whether its path may shift subtly over time, whether models of future motion are missing small but important effects. In that sense, Webb's observation of nearby minor bodies reveals something essential about the telescope itself. It is not only an instrument for turning the universe into distant history, it is also a tool for exposing the hidden complexity of the space already surrounding Earth. The same infrared sensitivity that reads ancient red-shifted light can also distinguish surface properties on a passing object that reflects almost nothing and moves against the stars with unsettling speed. What emerges from all of this is a portrait of the solar system that feels less settled than the textbooks once suggested. Neptune is active and textured. Chariklo wears rings it should not seem important enough to possess. Europa vents water from a hidden interior that may be exchanging material with an unseen ocean. Comets turn out not to be identical frozen relics, but chemically distinct histories in motion. The outer fringe of the solar system carries methanol and organics across bodies that should, by simple expectation, be too cold and remote to feel dynamic. Even near-Earth asteroids become richer and more revealing when observed properly. None of these discoveries alone overturns planetary science. Together they produce a subtler effect. They remove the illusion that the local cosmic neighborhood is already known in any complete sense. The solar system starts to look less like a finished map and more like an archive still being opened drawer by drawer. That change matters for the larger story Webb is telling. The telescope keeps proving that ignorance is not confined to the farthest reaches of space. Distance is only one kind of obscurity, another is habit. Scientists can become used to categories, used to broad descriptions, used to thinking that a body has already yielded its main meaning because it has already been named, measured, and placed in context. Webb keeps cutting through that comfort. It looks at what is nearby and shows that even the closest mysteries can remain hidden in plain sight. A moon can conceal an ocean and betray it only in a momentary plume. A centaur can possess rings. A comet can lack the volatile chemistry expected of its class. A distant planet in the solar system can still surprise with structure and atmospheric behavior despite centuries of observation. The effect is cumulative and quietly destabilizing. If even here, in the system where probes have flown and generations of astronomers have watched, the picture remains this unfinished, then the line between known and unknown is far thinner than it appears. The darkness does not begin beyond the solar system. It begins wherever the details have not yet been fully seen. By the time Webb begins sending back sustained deep field data, rather than single emblematic images, the discomfort becomes harder to dismiss as first-light excitement. A few suspiciously bright objects can always be treated with caution. Distances at the edge of the observable universe are difficult. Light is stretched, faint, filtered through dust, and interpreted through models that themselves carry assumptions. But as the surveys grow deeper and wider, the same tension begins appearing again and again. The telescope is not just finding ancient galaxies, it is finding too many of them, and too many of the wrong kind. Instead of a sparse population of dim, unfinished systems flickering weakly in the cosmic dawn, Webb starts revealing a crowd of compact, luminous, chemically busy galaxies appearing within the first few 100 million years after the Big Bang. They do not merely exist early, they look as though they have already been working for some time. This is what makes the problem so unsettling. Existence alone would be one thing, maturity is another. A galaxy can be present without being impressive. What Webb sees in some of these early systems is evidence of rapid assembly, dense stellar populations, and intense star formation that seems to have outrun the clock. The early universe begins to look less like an opening scene, and more like a world already underway before the audience has even taken its seat. The deeper surveys make this increasingly difficult to ignore. Programs such as the Cosmic Evolution Early Release Science Survey and the JWST Advanced Deep Extragalactic Survey are designed not for headlines but for sustained measurement. They gather light from carefully chosen fields, some of them already famous from earlier Hubble work, and then push into wavelengths where Webb is strongest. What returns is not chaos in the simple sense. It is structure, but structure arriving too soon. One candidate after another appears at redshift so high that its light must have left when the universe is only a few 100 million years old. Redshift, once translated into age, is meant to place objects on a cosmic timeline. The larger the redshift, the further back the telescope is seeing. For years, that timeline is populated mostly by expectations. The first stars ignite. Small halos merge. Galaxies assemble gradually, their mass and brightness rising with time. Webb does not erase that sequence, but it compresses it brutally. Galaxies that should still be assembling their first substantial populations of stars are instead shining with an intensity that suggests they have already built a great deal. Some look compact and dense, some appear to be forming stars at astonishing rates. Some show hints of chemical development that should require previous generations of stars to have already lived, died, and seeded the next round. Every one of those properties can be explained in isolation. Together they begin to feel like pressure on the entire timeline. One of the most discussed examples in the early Webb era is the object first identified as CERS 93316. At first, its estimated redshift places it at an almost absurd distance, implying that it exists roughly 235 million years after the Big Bang. Even later, refinements and debates over its exact nature do not remove the basic disturbance it represents. The mere fact that such candidates appear at all, bright enough to command attention, and plausible enough to survive serious analysis, means the deep universe is not behaving with the modesty earlier models encouraged. Whether any specific object is eventually reclassified matters less than the pattern established by many such discoveries. Webb keeps opening small windows into early cosmic time and finding not a few hesitant sparks, but entire systems already burning hard. That is why astronomers start speaking of a too early, too big problem. The phrase is informal, but the discomfort behind it is real. Galaxies appear more massive, more luminous, and more quickly organized than the standard expectations allow with ease. To understand why that matters, it helps to look at what a galaxy actually requires. A galaxy is not simply a cloud with light in it. Even the smallest early systems involve dark matter, halos gathering ordinary matter, gas cooling efficiently enough to collapse, stars igniting in large numbers, radiation pushing back, supernovae exploding, dust forming, feedback processes stirring the gas again, and gravity continuing to shape the whole system while the surrounding universe expands. Nothing about that sequence is instantaneous. In the conventional picture, the earliest epochs are constrained by time. There has simply not been enough of it. Yet Webb keeps finding galaxies that behave as if time has been less of an obstacle than assumed. It is as though the young universe has been caught skipping developmental stages. Instead of slow build-up, perhaps there are episodes of furious efficiency, dense regions where gas collapses into stars with a violence that older simulations do not fully capture. Perhaps the first stars, the so-called population 3 stars long, theorized, but not yet seen directly, are even more extreme in their effects than expected, seeding their environments with energy and heavy elements at extraordinary speed. Or perhaps the dark matter scaffolding of the young universe channels matter into place more effectively under early conditions than the simplified models suggest. None of these possibilities is impossible. What is disturbing is that they all require some widening of the old picture, and Webb seems to demand that widening repeatedly. Then the story becomes stranger. It is not only the brightness and abundance of early galaxies that unsettles astronomers, it is also their apparent shapes and internal coherence. In some cases, the systems do not look like ragged fragments barely beginning to exist. They look compact, settled, almost overdetermined, as if gravity and star formation have already spent hundreds of millions of years doing their work. The visual impression can be misleading, of course. Resolution at such distances is still limited, and careful measurement must always take precedence over human instinct. But the broader point survives caution. These galaxies are not presenting themselves as embryonic smudges alone. Many appear structured enough to raise the possibility that galaxy evolution begins with more speed and organization than anticipated. If that is true, then the young cosmos is not a gentle nursery. It is a place of immediate competition, collapse, ignition, and rapid differentiation. Matter does not hesitate. It rushes. The Jade's observations push this further by filling the deep fields with increasingly persuasive candidates at extreme redshifts. Some beyond 13, meaning that their light comes from a universe younger than roughly 330 million years. These are not mere single-pixel suggestions. They are bright enough, in some cases, to provoke serious attempts at spectroscopic confirmation and theoretical explanation. A standout case such as JADESGSZ 13-0 carries special weight not because it settles the issue on its own, but because it fits into the broader pattern. The early universe keeps yielding galaxies that seem far too capable. They are compact, luminous, and actively forming stars as if the raw materials of structure have been assembled with impossible haste. The old expectation that the first few 100 million years should host mostly tentative formation now begins to feel less like a law of nature and more like an assumption built from previous observational limits. Once a telescope exists that can actually look there with sufficient sensitivity, the assumption weakens. There is an almost unsettling symmetry to this. For decades, cosmology prides itself on being able to reconstruct the early universe from the present outward. It studies the cosmic microwave background, large-scale structure, nucleosynthesis, gravitational theory, and simulations of galaxy formation. The result is a framework of extraordinary power, and much of that framework still stands. Webb does not destroy it. The expansion of the universe remains real. The Big Bang remains the essential beginning of the observable cosmic story. Dark matter remains necessary. Yet within that larger success, the telescope finds seams. It discovers places where the details do not flow as smoothly as the broad narrative implies. This is often how science is truly challenged, not by total contradiction, but by local failures that reveal hidden simplifications. Webb is not showing that the cosmos is unrecognizable. It is showing that its early chapter may have been written in much greater haste and violence than anyone comfortably assumed. That growing tension leads to more adventurous possibilities. Some astronomers explore whether direct collapse events, where enormous gas clouds fall inward with unusual speed, might produce both stars and massive black hole seeds faster than gradual pathways permit. Others ask whether cooling processes in primordial gas are being underestimated, allowing dense clumps to form earlier and more efficiently. Some question whether the stellar populations in these first galaxies differ so strongly from later ones that ordinary brightness to mass conversions break down. If the first stars are hotter and more massive, a galaxy may appear more developed in light than it truly is in total assembled mass. That could ease the tension somewhat, but it does not remove the fundamental surprise. Even on generous interpretations, the early universe still seems crowded and busy. There is too much happening too soon. Then comes an even subtler disturbance, one that does not depend only on age estimates. When large enough samples of distant spiral galaxies are examined, claims emerge that their spin directions may not be distributed as evenly as expected. In one analysis of galaxies from the good south field, more spirals appear to rotate one way than the other. Such a result must be treated carefully. Sample sizes are limited. Classification methods can introduce bias. The motion of the Milky Way itself may influence brightness in ways that affect automated assessments. Yet even the appearance of such a pattern is provocative, because standard cosmology assumes large-scale isotropy. The idea that the universe has no preferred direction when viewed on sufficiently large scales. A significant asymmetry in spin would not automatically overturn that principle, but it would invite uncomfortable questions. Is there a hidden bias in observation? Is there a subtle selection effect in the data? Or is there some trace of a larger primordial order, something imprinted in the universe before galaxies fully formed? The more conventional explanations remain stronger for now, but the very fact that such speculation becomes thinkable tells its own story. Webb is not simply adding detail. It is reviving questions that sound almost archaic, as though the universe may still conceal directional memory from an origin far stranger than the standard picture prefers to imagine. And still, the deeper emotional effect comes not from any single anomaly, but from accumulation. Every new deep field seems to weaken the image of a slow beginning. Every newly confirmed early galaxy makes the first few 100 million years look more populated. Every especially bright candidate implies that stars are turning on with ferocity, that black holes may be growing in parallel, that dust and heavy elements may be appearing on accelerated schedules. The infant universe, once described in careful language as a gradual emergence from darkness, begins to resemble something more abrupt, almost explosive in its complexity. Not the Big Bang itself, but the aftermath, the onset of structure, the turning on of light. Webb suggests that this turning on may have happened with astonishing speed, perhaps so fast that some of the old categories of early, middle, and mature cosmic growth blur into one another. Galaxies do not merely arrive. They arrive in a state that forces astronomy to ask whether its clocks have been too polite. That is where the section of the story truly darkens, because once galaxies are found to be too luminous and too abundant too soon, the problem does not remain confined to galaxies. It spills outward into everything that should accompany them. If those systems are already there, then where are the black holes that ought to be growing at their centres? If stars are forming that fast, what is regulating them, if anything? If heavy elements are already appearing, how many generations of stellar death have already passed in secret? Each answer threatens to lead not toward closure, but toward another acceleration somewhere else in the chain. The universe Webb reveals at high redshift is not merely older looking than expected. It is more active, more efficient, and perhaps more extreme in its earliest behaviour. That is the disturbing part. The deeper the telescope looks, the less the beginning resembles a quiet beginning at all. At first, the trouble seems limited to timing. Galaxies appear too bright, too numerous, too mature, and so the obvious conclusion is that the early universe simply builds structure faster than expected. But then another kind of anomaly begins to gather around the data, and this one is harder to absorb into a simple story of accelerated growth. It is not just a question of when galaxies form, it is a question of whether the universe is arranging them with a faint preference, a slight lean, a directional memory that standard cosmology does not expect to find. The possibility appears in a quiet way, buried inside classification work that on the surface seems technical and almost routine. Astronomers examine distant spiral galaxies in deep survey fields and ask which way they appear to rotate, clockwise from the perspective of Earth, or counterclockwise, in a perfectly isotropic universe, meaning one that has no preferred direction on large scales. Those orientations should balance out statistically when enough galaxies are counted. Any small mismatch should wash away with larger samples, dissolving into randomness. Instead, in some analyses of distant Webb data, especially in the good south field, the balance does not look quite right. There appears to be an excess of spirals turning one way over the other, not an overwhelming domination, not a result so definitive that it overturns anything by itself, but enough of an imbalance to feel irritating in the way that all stubborn anomalies do. It refuses to disappear immediately. It hangs there in the numbers like a question the universe is not yet ready to answer cleanly. The significance of that depends on what the imbalance really is. The most cautious interpretation is also the most ordinary. Observations of the deep universe are difficult. Distant galaxies are faint, small, and distorted by both instrumental limitations and cosmic effects. Classifying spiral direction at high redshift is not like sorting large, nearby galaxies with clear arms and stable geometry. Algorithms must infer patterns from partial light. Noise can matter. Orientation can be ambiguous. Human intuition can fail. Even the motion of the Milky Way through space might create tiny brightness asymmetries through Doppler effects that subtly bias which galaxies are easier to classify in one direction rather than another. These explanations are not desperate excuses, they are serious possibilities, and astronomy is right to consider them first. Yet what makes the issue interesting is not that it proves a preferred cosmic direction. It is that the door to such a possibility has been opened at all. Once the early universe starts producing not only galaxies that form too quickly, but distributions that may not be as directionless as expected, the conceptual ground begins to shift. The question is no longer only whether cosmic history is faster than the models suggest. It becomes whether the large-scale framework itself carries a hidden asymmetry. That is a much older and stranger possibility than it first sounds. Modern cosmology rests heavily on the cosmological principle, the assumption that on sufficiently large scales the universe is homogeneous and isotropic. In plain terms, it means that the universe has no special center and no preferred direction. Look far enough out, average enough galaxies together, and the cosmos should appear broadly the same whichever way the telescope turns. This principle does not claim that everything is locally uniform. Galaxy clusters, voids, filaments, and violent mergers obviously exist. But taken on the grandest scales, the universe should not tilt. It should not favour one cosmic handedness over another. It should not carry a detectable spin written across the sky. That assumption has served cosmology well because much of the large-scale evidence supports it. The cosmic microwave background is remarkably uniform. The distribution of galaxies on the larger scales broadly fits the expectation of statistical symmetry, and yet the principle is still, in the end, an inference drawn from data. It is not a sacred law protected from challenge. If sufficiently good observations begin to hint that the universe is not as directionless as believed, then the challenge would cut deeper than the problem of early bright galaxies. It would touch the shape of the framework itself. The reason this becomes so unsettling in the Webb era is that the telescope is probing regions of time where the universe is still young enough that any primordial asymmetry might be easier to spot. Later cosmic history is complicated. Billions of years of mergers, feedback, clustering, and environmental influence can blur earlier signals. But in the distant past, some traces of the original conditions may remain less diluted. That is why even a tentative spin imbalance feels provocative. It raises the possibility that what is being seen is not merely the chaos of galaxy formation, but a faint imprint of something deeper, something present before galaxies fully separate into the forms now observed. It is here that speculation begins to widen. Some theorists entertain unconventional ideas, including scenarios in which the universe inherits rotational properties from a more exotic origin. One of the more dramatic concepts imagines that the observable universe forms inside a black hole embedded in a larger parent cosmos, with angular momentum from that larger structure leaving a subtle mark on the baby universe inside. This remains far outside mainstream acceptance, and for good reason. It is highly speculative, difficult to test directly, and vulnerable to the temptation of explaining one mystery by creating a larger one. Still, the fact that such ideas re-enter discussion at all shows how destabilizing these fainter symmetries can be. A small pattern in spiral directions may not mean very much, but if it survives scrutiny, it begins to invite explanations far more radical than anyone expected when Webb was first sent into space. Even without those more extreme possibilities, the pattern forces astronomy to confront a simpler discomfort. Perhaps the early universe is not merely more active than predicted. Perhaps it is more organized in ways the current models only partially capture. The standard picture of structure formation begins with tiny density fluctuations in the early cosmos, fluctuations amplified by gravity until matter gathers into halos, stars ignite and galaxies emerge. This process is statistical, distributed, and in the broadest sense directionless. But if the first galaxies appear with surprising coherence, rapid maturity, and perhaps even a mild directional bias in their spins, then it becomes possible that the primordial conditions feeding galaxy formation are richer than expected. Maybe the density field contains subtleties not adequately resolved. Maybe early interactions between radiation, ordinary matter, and dark matter generate patterns that later averaging hides. Maybe what is being interpreted as randomness contains weak preferences that only become visible when instruments are finally sensitive enough to stare deeply and long enough into the same small patches of sky. The intriguing part is that this question arrives on top of the already unresolved timing problem. If the early universe is simply faster, that is one kind of revision. It means matter collapses efficiently, stars ignite sooner, galaxies build rapidly, and black holes may follow. But if the early universe is also less isotropic than assumed, then the revision becomes broader and more unsettling. It suggests not only a change in pace, but a change in architecture. The old image of cosmic dawn as a mostly uniform darkness gradually punctured by the first lights gives way to something more dynamic, perhaps even slightly patterned from the beginning. This does not mean the universe suddenly acquires an obvious axis or behaves like a spinning wheel. The possible asymmetries are subtle, statistical, and easily overstated. Yet subtlety is often exactly how deep truths first appear, not as dramatic violations, but as small, stubborn mismatches between what should average out and what does not. Webb's role in this is almost paradoxical. It is a telescope built to make the invisible visible, to refine blurry guesses into measured evidence, and that is precisely what makes the resulting uncertainty more powerful. An anomaly born from weak data can be ignored. An anomaly born from improved clarity is harder to dismiss. This is the same pattern seen in the first deep field, the same pattern seen in early galaxy counts, the same pattern seen in exoplanet atmospheres. Better observation does not simplify the universe. It sharpens the point at which the universe stops agreeing with expectation. In the case of possible spin asymmetry, the data may yet retreat into ordinary explanation. Larger samples may smooth the imbalance away. Classification methods may improve. Selection biases may reveal themselves and strip the mystery back to a statistical mirage. That remains entirely possible. But even in that outcome, something important has already happened. Webb has pushed cosmology into a position where it must test one of its deepest assumptions against direct observation in an era of cosmic history it has barely seen before. And the universe, at least for now, is not making that test easy. The deep fields remain crowded with early galaxies. Their brightness still strains the timelines. Their abundance still complicates formation models. Their spins, or apparent spins, may or may not lean in unexpected ways. Every piece of this could, in isolation, be absorbed. Together they begin to create a mood that is difficult to ignore. The early universe no longer looks like an uncomplicated proving ground for well-behaved theory. It looks like a place where the old assumptions are being stressed all at once. The trouble is not only that galaxies appear too soon, it is that when they do appear, they bring with them hints that the cosmos may not be as indifferent in direction as expected. A slight excess here, a structural maturity there, a density of objects where emptiness was expected, and suddenly the earliest epochs of cosmic history feel less like a blank page and more like a page already covered in faint writing, visible only now that the light is strong enough to read it, if that impression holds, even partially. Then the phrase deep field begins to mean something more than a technical term for a long exposure on a tiny part of the sky. It becomes a kind of excavation. Webb is not only looking far away, it is digging into the assumptions beneath cosmology, layer by layer, finding beneath them not a clean foundation, but a surface scored with unresolved marks. Some will turn out to be artifacts, some will fade under better measurement, but some may remain. And the possibility that the universe has preserved a directional trace from its earlier structure is one of the most unnerving of all. Because if the cosmos really does lean, even slightly, then the darkness at the beginning is not just full of early galaxies, it is full of memory. Once the early galaxies begin to look too bright and too complete for their age, another question rises behind them almost automatically. If these systems are already assembling stars at such speed, then what is happening in their centres, in the modern universe? Large galaxies and supermassive black holes seem tied together by a relationship that is still not fully understood, but impossible to ignore. Nearly every substantial galaxy appears to host one of these central objects, sometimes quiet, sometimes actively feeding, sometimes hidden behind gas and dust, sometimes blazing so brightly that the black hole's surroundings outshine the entire galaxy around it. The old problem has never been whether such black holes exist. It has been how they became so enormous. A black hole born from a massive star begins small by cosmic standards. To grow into a monster millions or billions of times heavier than the Sun, it must feed, merge, and survive long spans of time. That process is already difficult to explain in the later universe. Webb pushes the puzzle backward into the earliest epochs and makes it far worse. If galaxies are arriving too soon, then black holes may be arriving too soon as well. And unlike a bright early galaxy, which can sometimes be reinterpreted through stellar population assumptions or mass estimates, a feeding black hole is hard to domesticate. When it is active, it announces itself through energy, through emission lines, through the unmistakable violence of matter falling inward and heating beyond imagination. In other words, if Webb sees black holes already feeding in the early universe, then something in the timeline is not merely compressed, it is under strain. That strain becomes visible in objects such as CEERS 1019, a galaxy from a time when the universe is only around 570 million years old. Webb identifies the signs of an active galactic nucleus there, meaning a central black hole is already accreting matter, not dormant, not hypothetical, not waiting for the surrounding galaxy to mature, feeding. The estimated mass of the black hole is not among the largest ever found, which in some sense makes the discovery more interesting rather than less. A modest early black hole still forces the same question. How does a black hole form, acquire mass, and settle into the centre of a galaxy quickly enough to be visibly active at such an early stage? It implies that the pathways toward black hole growth are already open when cosmic history should still be struggling through its first structural chapter. That is the essential disturbance Webb introduces here. It does not merely reveal ancient black holes as curiosities, it reveals them as participants in the early assembly of the universe, already taking part in the processes that shape galaxies before the models are fully ready to accommodate them. This is where the long-standing debate over black hole seeds becomes impossible to avoid. There are two broad ideas, though reality may involve more than either one alone. In one picture, black holes begin as the remnants of the first massive stars. Those stars live fast and die violently, leaving compact remnants that grow over time by swallowing gas and merging with one another. This is the more intuitive path, because it builds from known stellar processes. But it is slow. There are limits to how fast a black hole can feed before radiation from infalling matter pushes material away and chokes the growth. Even under favourable conditions, turning a stellar remnant into a supermassive object within the first several 100 million years is difficult. The second picture is more drastic. In this idea, some black holes are born large through direct collapse. Instead of waiting for stars to form first, enormous clouds of gas collapse almost wholesale under the right conditions, avoiding fragmentation and creating a massive seed black hole from the start. That route is violent, rare, and not yet directly confirmed. But Webb's early black holes keep making it look less like an extravagant fantasy, and more like a possibility that the universe may have exploited when time was short. The telescope does not prove direct collapse. What it does is remove some of the comfort from slower explanations. The early universe keeps presenting black holes that seem impatient. Then there are the quasars, the brightest of all these signs. A quasar is not the black hole itself, but the furnace around it, a region wherein falling gas heats so intensely that it floods space with radiation. Quasars can be seen across immense distances precisely because they're so outrageously luminous. They are cosmic lighthouses, but they are also warnings. Each one marks a black hole in a state of voracious growth. When Webb looks at quasars more than 13 billion light-years away, it is not simply cataloguing bright points in the dark, it is looking at engines already running near the dawn of structure. One of the striking cases in this broader picture involves the quasar in J0439 plus 1634, whose light is magnified by gravitational lensing. A foreground mass bends and amplifies the radiation, allowing a clearer look into a system that would otherwise be more difficult to study. Again, gravitational lensing acts as both trick and revelation. Space itself distorts the image, yet that distortion becomes the instrument by which the ancient universe is exposed, and what it reveals is not a primitive object patiently awaiting its era. It reveals a black hole already consuming matter with astonishing efficiency in a universe still younger than the old models would comfortably permit. That is where black holes begin to feel less like secondary complications and more like central actors in the unfolding mystery. If the first galaxies are too bright, perhaps intense star formation explains some of it. If their masses are overestimated, perhaps unusual early stellar populations reduce the tension. But when black holes join the story, feeding actively and radiating fiercely, the problem widens. Black holes influence their surroundings. Their radiation can ionize gas, drive winds, regulate star formation, and reshape the central regions of galaxies. They are not passive consequences of growth. They are participants in it. That means the early universe may not simply be evolving faster. It may be entering a feedback-rich state far sooner than anticipated, with galaxies and black holes growing together in tight and violent partnership, almost from the start. In that picture, cosmic dawn becomes less like a sequence of isolated firsts and more like a cascade. Gas collapses, stars ignite, black holes form, radiation pours outward, matter is stirred, heated, expelled, and drawn inward again. Whole systems accelerate together. The deep discomfort comes from how little room for delay this leaves. A black hole that is already visibly active less than 600 million years after the Big Bang implies earlier precursor stages that disappear further into the dark. The seed must form before the feeding phase. The galaxy must already contain gas dense enough to supply it. Surrounding stars must already be present or forming in tandem. By the time Webb sees the signal, the hidden preparation has already happened. The telescope is therefore catching not the beginning of the process, but a stage already underway, and once that is recognized, the question becomes almost impossible to avoid. How much happened before the earliest clear observations now in hand? If the first directly observed active black holes are already mature enough to feed, what lies only slightly earlier, just beyond present reach? Are there darker stages of collapse and growth that begin almost immediately after the first stars? Are there massive seed black holes forming in the densest primordial regions before the rest of the universe has meaningfully awakened? The image of a gradual dawn starts to fail again. The first light may not be the first event at all. It may be the visible consequence of processes that have already raced ahead in hidden corners. Gravitational lensing intensifies this feeling because it reveals how much of the distant universe is accessible only through distortion. A lensed quasar is not merely magnified. It arrives by multiple paths through curved space, sometimes stretched, sometimes split, sometimes delayed. The light that reaches Earth is already a rearranged version of the event. Webb turns those rearrangements into tools. The telescope can separate faint details, identify the host structures, and help astronomers estimate both the source and the lens. In doing so, it exposes not just individual ancient black holes, but the strange geometry of observing them. The universe is so deep and so structured that even its most distant active objects must often be read through intervening mass. It is as if the cosmos is reluctant to yield its earliest engines directly. They appear through bending, amplification, and time delay, as though the act of looking into the far past requires passing through layers of later structure that themselves participate in the message. That layered geometry becomes especially haunting when it leads to transient events like the lensed supernova nicknamed Esna-Zerup. Webb observes the same exploding star appearing in multiple images because the light has travelled along different routes around a massive foreground cluster. Each route takes a different amount of time. The result is a cosmic replay, the same event arriving not once but in separated glimpses. This is scientifically powerful because such systems can help measure the expansion rate of the universe. Feeding directly into the unresolved Hubble tension, the disagreement between different methods of determining how fast space is expanding today. But the deeper mood of the observation is stranger than the method. A star dies once, yet the universe presents that death several times, delayed and displaced by gravity. Past events echo. Time does not arrive in a single stream when mass intervenes. Webb, built to observe ancient light, ends up catching the cosmos, revealing one of its more unsettling habits. Even history can split. That matters because the black hole problem is ultimately also a problem of timing. How fast can matter gather? How early can structure ignite? How soon can enormous central objects appear? Every lensed quasar and multiply image transient reinforces the fact that time in cosmology is not simply counted, but inferred through light that has been bent, reddened, delayed, and filtered through intervening structure. The confidence of modern astronomy rests on learning how to decode those transformations. Webb improves that decoding immensely, but it also makes the decoded picture harder to reconcile. Black holes appear early, galaxies appear mature, explosions from the deep universe arrive in copied sequences through warped space. Measurements that should bring closure instead multiply the number of places where theory must catch up. Then another twist arrives. Some of the galaxies Webb identifies in the early universe are not in states of furious ongoing star formation at all. They appear to have already gone quiet, their brightest youthful phase apparently over. Before the black hole story can settle, the galaxy story mutates again. The early cosmos is no longer just full of systems growing too fast. It is beginning to show signs of systems that have already burned through their active youth and entered silence before they should have had time to do either. If galaxies can form rapidly enough to host feeding black holes, perhaps they can also exhaust themselves with equal speed. The logic is brutal. The same universe that produces monsters before its schedule also produces exhaustion before its schedule. Webb is not merely finding early life in the cosmos. It is finding early overdevelopment, early appetite, and perhaps early burnout. The darkness between galaxies begins to feel less like empty background and more like the unlit space between processes that happen too quickly to observe in full. The strangest part is that the early universe does not merely seem fast, it also seems tired, after galaxies that appear too bright, black holes that begin feeding too soon, and deep fields crowded with systems that look more advanced than expected. Webb starts uncovering another category of object that feels almost misplaced in time. These are galaxies that are not erupting with new stars, not swelling with obvious fresh birth, not glowing with the usual signs of abundant cold gas ready to collapse again. They appear quiet. In astronomy, the term is quiescent, which sounds almost gentle, but the reality behind it is severe. A quiescent galaxy is one that has largely stopped forming stars. Its bright youth has passed, or at least paused. The raw material of future stellar birth has been heated, blown out, exhausted, or locked away. In the nearby universe, Such galaxies are familiar enough. Many large elliptical systems are dominated by older stellar populations and show little active star formation. Time has had room to do its work there. Mergers have occurred, gas has been consumed or expelled. Central black holes may have helped suppress fresh collapse. The long, messy adolescence of a galaxy has, in effect, ended. But when Webb begins finding galaxies in the first billion years of cosmic history that already look silent, the old sequence starts to feel broken in a new way. It is one thing for the universe to grow up too fast. It is another for parts of it to already seem old. That is why these objects are so disorienting. They do not just compress the timetable of galaxy formation. They compress the timetable of galaxy exhaustion. Some of the galaxies Webb observes from well within the universe's first billion years appear to have already gone through an intense period of star formation and then shut much of it down. The phrase Sleeping Beauty galaxies begins to circulate, half poetic, half clinical, because the systems seem dormant rather than dead, as though they may be capable of waking again if fresh gas becomes available. But even the softer wording cannot hide the difficulty they create. Standard expectations do allow for feedback, violent bursts, and environmental effects. Yet those mechanisms are usually imagined as playing out over longer spans. A young universe should still be in a phase of abundant assembly. Matter is gathering into halos. Gas is cooling. Stars are turning on across newly formed systems. There should be noise everywhere, a great unfinished rush. And yet Webb sees some galaxies that seem to have already passed through their loudest phase and into a kind of early stillness. The image is almost absurd. It is like walking into a city on the day it is founded and already finding abandoned districts. The evidence for quiescence is not based on a single dramatic picture, but on the quieter language of colour, spectra, and stellar population modelling. A galaxy dominated by young, hot stars looks different from one whose light comes mainly from older populations. Ongoing star formation leaves certain signatures: dust, gas, and the age distribution of stars all shape the light that reaches the telescope. Webb is particularly good at tracing these distinctions in the infrared, where the red-shifted light of early galaxies can be separated and analysed more effectively than before. When the light from some of these ancient systems is interpreted, the result suggests that their main star-forming episode happened earlier and more intensely than expected, followed by a decline or shutdown in fresh stellar production. That interpretation is not casual. It carries uncertainties, as all deep universe reconstruction does. Dust can mimic age in some cases. Burst histories can be difficult to disentangle. A galaxy may not be fully dead, only greatly diminished in its current formation rate. But even allowing for those caveats, the existence of multiple candidates pointing in the same direction is hard to ignore. The early universe is not just producing galaxies quickly, it is producing galaxies quickly enough for some to already begin aging. This creates a new kind of pressure on theory. A galaxy cannot become quiescent without first becoming active enough for quiescence to mean something. Silence implies a previous noise. A shutdown implies a prior blaze. If a galaxy in the early universe already contains a substantial population of older stars and little sign of ongoing formation, then it must have formed those stars at extraordinary speed beforehand. That means the too early, too big problem gains another dimension. It is no longer only about building mass too soon. It is about building mass, burning through gas, and then suppressing further growth on an impossible schedule. Whatever is driving these galaxies does not merely accelerate them into existence. It may be pushing them through whole life stages in rapid succession. Birth, flare, and dormancy all seem capable of unfolding in a fraction of the time once assumed necessary. There are several ways such a thing might happen, none fully satisfying on its own. One possibility is that early galaxies experience starbursts so violent that they consume their available gas with astonishing efficiency. If gas collapses quickly enough in dense primordial environments, perhaps the resulting stellar production is not steady but explosive. A brief furnace that turns a large fraction of the material into stars and leaves relatively little behind. Another possibility is feedback. Newly formed stars, especially massive ones, produce intense radiation, stellar winds, and supernova explosions. A feeding central black hole can add even more energy. Together, these processes can heat or expel gas, making it difficult for the galaxy to continue forming stars at the same pace. In the later universe, feedback is already considered essential for understanding why galaxies do not simply turn all their gas into stars forever. But Webb suggests that in the earliest epochs, feedback may become important far sooner and more brutally than anticipated. Instead of serving as a late regulatory mechanism, it may be part of the opening act. There is also the role of environment. The early universe is not smooth in any practical sense. Matter gathers unevenly. Some regions become overdense, rich in collisions and inflows, while others remain comparatively sparse. A galaxy born in a particularly crowded and violent environment may experience rapid growth, followed by equally rapid disruption. Mergers can trigger starbursts, then destabilize gas reservoirs. Tidal interactions can rearrange material. Shock heating in dense halos can interfere with fresh cooling. In that case, quiescent early galaxies are not evidence of universal behavior, but of extreme local pathways, systems born in the most intense neighborhoods, and therefore pushed hardest by the forces around them. Yet even that explanation does not reduce the mystery much. It still means the young universe is capable of creating mature-looking, partially exhausted systems with unnerving speed. The question changes from how can any galaxy do this to how common are the conditions that allow it. Webb's discoveries keep making that second question harder to answer comfortably. The more the telescope observes, the less these silent systems look like isolated accidents. They may remain rare compared with all galaxies at the time, but rarity does not make them less important. In astronomy, rare objects are often the most revealing because they expose the full range of what nature permits. A single early quiescent galaxy is already a challenge. Several begin to suggest a population. A population implies a process, and once a process exists, even if it operates under extreme conditions, the universe must make room for it in its broader story. That is where the old linear narrative begins to break apart. Cosmic dawn is no longer a simple transition from no galaxies to young galaxies to mature galaxies in tidy order. Webb is showing overlap instead. At the same early time, some systems are still building, some are already blazing, some host active black holes, and some may already be winding down. The universe's opening centuries look less like a sequence of chapters and more like many chapters unfolding at once. This overlap has a deeper consequence. It suggests that early cosmic history may be governed less by a universal pace than by a wide spread of local tempos. Some halos collapse early and violently. Some remain quiet longer. Some galaxies become nurseries. Some become furnaces. Some may briefly become both before their conditions change. In that framework, the early universe is not a single synchronized dawn, but a patchwork of accelerations. Certain regions race ahead, others lag. The result, when viewed through Webb, is unsettling because it makes the young cosmos look less like an orderly beginning and more like a landscape already differentiated by fate. One part of the sky may hold systems barely emerging. Another may hold galaxies that already seem to have lived too much. The presence of early quiescent galaxies also sharpens the black hole question rather than separating from it. If feedback is one route to shutting down star formation, then central black holes may be partly responsible. A black hole accreting vigorously can release enough energy to disturb or remove the gas that would otherwise collapse into new stars. In nearby galaxies, such feedback is often invoked to explain why some massive systems remain quiescent. If something similar is already operating in the first billion years, then black holes are not just arriving early. They're already influencing the life cycles of galaxies around them. This would make the early universe even more interconnected than expected. Star formation feeds black hole growth. Black hole growth suppresses star formation. Galaxies flare, then quiet. The machinery of maturity is present almost immediately. What once seemed like the middle age of cosmic evolution may, in some regions, begin right near the beginning, and that, perhaps, is the most disturbing shift Webb introduces here. It forces astronomy to stop imagining youth as a uniform state. The old assumption carries an emotional logic as much as a scientific one. Early means simple. Early means unfinished. Early means raw potential rather than completed consequence. But the telescope keeps showing the opposite. Early can mean overdeveloped. Early can mean chemically enriched. Early can mean centrally active, structurally compact, and already fading in places. The universe does not grant itself a long innocent phase. It moves directly into complexity, and in some cases directly into decline. It is not merely that galaxies grow faster than expected, it is that they seem capable of living too much too soon. The unsettling calm of these galaxies makes them feel almost ghostly in Webb's data. Bright early galaxies at least fit an image of cosmic energy, of furious creation under dense primordial conditions. Quiescent early galaxies feel colder. They suggest that some systems have already used up or lost what they needed most. Their light is ancient in two senses at once. It comes from far away, and it seems to come from stars already old for their time. That dual age is what makes them so haunting. They are not relics from the later universe seen nearby. They are old-seeming systems embedded inside the era that was supposed to still be young. There is room for caution, and astronomy takes it. Better spectra are needed. Larger samples matter. Dust and observational bias must be handled carefully. Some apparently quiescent galaxies may turn out to be more complicated, partly obscured rather than truly dormant, or caught in temporary lulls rather than full shutdowns. But caution does not erase the direction of the evidence. Webb has opened a region of cosmic history where surprise keeps arriving in the same emotional register. The earliest epochs are fuller, faster, brighter, and now quieter than they should comfortably be. Every time the telescope resolves another one of these silent systems, it adds to the sense that the first billion years are not just inadequately understood, but fundamentally more varied than expected. And variation at that level changes the meaning of everything around it. If some galaxies can already go dormant so early, then the pathways toward habitability, chemical enrichment, and large-scale structure are all affected. Dormant galaxies produce fewer new stars, fewer fresh planetary systems, and different radiation environments. Their history of starbursts may flood surrounding space with heavy elements and then fall silent. Their black holes may continue to shape their centers long after star formation fades, even if no single early quiescent galaxy rewrites cosmology by itself. Together they alter the texture of cosmic dawn. They make it feel less like the first morning of the universe and more like a day already well underway in some places, already beginning to dim in others. The light is no longer simply turning on. In parts of the young cosmos, it may already be going out. Then the story narrows to a single planet, and for a moment the scale of the mystery changes. It is no longer about whole populations of galaxies arriving too soon, or black holes feeding before their time, or silent systems already exhausted in the first billion years. It is about a world, a distant one, still impossible to see directly as a round globe with continents or clouds drifting across a visible disk, but a world nonetheless, orbiting a cool red dwarf star roughly 120 light-years from Earth in the constellation Leo. Its name is K218b. Before Webb studies it in detail, the planet is already known as an interesting place. It sits in what is broadly called the habitable zone, the region around a star where temperatures might allow liquid water under the right conditions. It is larger than Earth, smaller than Neptune, and awkwardly placed between categories: too massive to be comfortably Earth-like, too compact to be dismissed as just another gas giant. Earlier observations hint at water vapour in its atmosphere, and that is enough to keep the planet in circulation among astronomers interested in future habitability studies. But hints are not the same as atmosphere, and atmosphere is not the same as biology. For years, the field of exoplanet science has lived in that gap, where promising language can easily outrun the evidence. Webb enters the picture and, for the first time, the gap begins to narrow in a way that feels almost dangerous. The reason it feels dangerous is not because Webb proves life exists there. It does not. The data does not permit anything so final, and the careful scientific response remains cautious throughout. What the telescope does instead is arguably more unsettling. It produces a combination of atmospheric signals that is difficult to ignore and difficult to interpret cleanly. Methane appears, carbon dioxide appears. The broader atmospheric context seems consistent with a hydrogen-rich environment that may sit above a deep ocean, though that interpretation remains debated. And then there are the possible signs of dimethyl sulfide, along with attention given to dimethyl disulfide as well. On Earth, dimethyl sulfide is associated with biology, especially with marine microorganisms. It is not a universal marker of life in all conceivable chemistries, nor is Earth a perfect template for what biology elsewhere must do. Yet within known Earth chemistry, dimethyl sulfide is striking because there is no well-established large-scale non-biological source for it at the surface and in the atmosphere under ordinary conditions. That is what gives the Webb observations their power. The telescope does not hand astronomy a declaration. It hands it a molecule that, on Earth, is entangled with life strongly enough to make the entire field stop and lean closer. This is where the documentary tone of speculation becomes almost impossible to resist. And yet the science is most interesting precisely where it resists easy escalation. K218b is not a second Earth. Even the most generous models do not portray it that way. It may be what some researchers call a Hycean world, meaning a planet with a hydrogen-rich atmosphere and the possibility of a deep global ocean beneath. If that picture is correct, then the environment there is unlike anything on Earth in its bulk properties, pressure conditions, and atmospheric behaviour. It may have no solid surface in the ordinary sense accessible to life as humans usually imagine it. Its ocean, if it exists, may be extremely deep. Its atmosphere may be thick, warm, and chemically active in unfamiliar ways. Even its star complicates things, because red dwarfs can be volatile, capable of flares and energetic events that influence planetary atmospheres over long stretches of time. All of that matters because the moment a possible biosignature is mentioned, the real scientific burden becomes context. A molecule does not mean the same thing everywhere. Life is not inferred from one gas alone. It is inferred, if ever, from combinations that are difficult to sustain without ongoing replenishment, from environmental settings that can plausibly host stable chemistry, and from the failure of non-biological explanations to account for what is seen. Webb's data on K218b is important because it begins to make that kind of discussion real, rather than purely theoretical. It does not solve the problem of life detection, it starts the problem in earnest. That is why the observation feels like a threshold. For decades, speculation about extraterrestrial life in exoplanet research has rested on broad probability. There are many stars, there are many planets. Some fraction may be temperate, some fraction may have atmospheres. Somewhere, perhaps, biology begins. It is a powerful statistical argument, but it remains distant. K218b changes the emotional texture of that argument because it concentrates attention on one actual atmosphere and one actual set of molecules. The discussion is no longer only about how life might be common in principle. It is about whether a specific world may be carrying a chemical pattern that, under at least one known planetary biology, would be hard to dismiss. That changes the mood entirely. Probability becomes proximity, not in physical distance, because 120 light-years is still enormous, but in interpretive distance. The idea of alien biology moves one step closer to data, and yet uncertainty immediately widens around that very step. Dimethyl sulfide is not magic, it is chemistry. If nature can produce it biologically, perhaps under different conditions it can also produce it abiotically, through pathways not yet fully understood. A hydrogen-rich atmosphere under intense radiation may allow reactions not familiar from Earth's air. The pressures and temperatures on a world like K218b may open chemical routes that laboratory intuition has barely explored. Clouds can interfere, retrieval models can differ, spectral features can overlap. Instruments, however powerful, still read atmospheres as filtered patterns in starlight, not as direct samples in a flask. So even as excitement builds, a deeper uncertainty sets in. The possible biosignature is compelling not because it is definitive, but because it occupies a narrow and difficult territory between noise and proof, too suggestive to ignore, too incomplete to trust completely. That is the most scientifically honest and narratively unsettling place an observation can live. In some ways, K218b becomes the perfect Webb discovery because it repeats the telescope's larger pattern in miniature. The instrument looks at something long discussed in broad and hopeful terms, then replaces the hopeful vagueness with sharper evidence that makes the mystery harder rather than easier. Before Webb, the planet is interesting. After Webb, it is problematic. Its atmosphere no longer serves as a blank screen for speculation. It becomes a real environment with real chemical tension. Methane and carbon dioxide in the same atmosphere matter because they can point toward disequilibrium, a state where gases coexist in ways that often require ongoing processes to maintain them. Add a possible sulfur-bearing molecule associated on Earth with marine life, and the planet begins to acquire a kind of scientific gravity. Not proof, not certainty, but gravity. It starts pulling attention toward itself because it demands better explanations than optimism alone can provide. That demand is what makes the result more disturbing than triumphant. A clean detection of an obviously non-biological atmosphere on a distant world would be easier to absorb. Even a null result would be simpler. But a world that sits just inside interpretive reach, offering chemistry that could mean life, or could mean an unknown planetary process, creates a more durable tension. It forces astronomy into a new phase of discipline. The field can no longer speak about biosignatures as abstractions alone. It must now decide how much weight a suggestive molecule should carry when placed inside an atmosphere unlike Earth's. It must build models not just of what life produces, but of what strange planets produce without life. In a quiet way, that may be one of Webb's most important effects. It does not simply increase the chance of finding life. It increases the need to understand lifeless worlds well enough not to mistake them for living ones. The planet itself becomes stranger the longer it is considered. If the Heysian interpretation is correct, then beneath the atmosphere there may be a vast ocean covered by thick clouds, perhaps dimly lit through a reddish stellar spectrum. perhaps stirred by pressures and temperatures unlike those in any Earth ocean. No one knows what chemistry such an environment would favour over geological time. No one knows whether life, if it emerges there, would be more likely to flourish in a hidden water layer, to remain chemically subtle, or to alter the atmosphere in a way telescopes could actually detect. And if K218b is not a water-rich world after all, if later analyses reshape its atmospheric interpretation, then the mystery only changes form. It would remain a planet whose chemistry fooled human expectation, a reminder that the road to identifying life runs directly through the problem of understanding planets that do not resemble the solar system closely enough to reassure anyone. That is why the observation does not feel like an ending. It feels like a beginning made of restraint. The headlines outside science may rush toward declarations, but the deeper story is slower and stranger. For the first time, a telescope has provided enough atmospheric detail on a distant temperate world to make the phrase sign of life sound less like fantasy and more like a provisional scientific question. That alone is a profound change. The question is no longer whether biosignatures can ever be sought on exoplanets. It is how to live with the first serious candidate clues without turning them into certainty too soon. Webb has brought the field to that edge, and standing there reveals how little preparation certainty would actually have. If stronger evidence appears later, astronomy will have to decide what counts as enough. If the signal fades under reanalysis, it will have to confront how easily hope can attach itself to incomplete patterns. In either case, 218b remains a turning point because it has shown that the universe is now capable of answering the question in fragments, and fragments can be more unnerving than silence. Silence leaves room for imagination. Fragments leave room for misinterpretation, revision, and return. A possible sulfur signal in a distant sky is exactly that kind of fragment. It is small, indirect, fragile, and yet impossible to forget once seen. The telescope that found galaxies too early and black holes too soon has now found something else just as unsettling, a world whose atmosphere may be whispering in a language science has only just begun to learn how to hear. Whether that whisper belongs to biology, chemistry, or some third process not yet understood remains unresolved. But the important fact is that the whisper exists at all. The sky of another planet is no longer mute. It contains clues that matter enough to change how the search for life is conducted from this point onward, and if a single planet 120 light-years away can generate this much ambiguity, then the galaxy may be full of atmospheres already waiting with signals that are just as suggestive, just as elusive, and just as difficult to trust. As the years of observation continue, another pattern begins to emerge. One less about any single category of object and more about the strange consistency of the surprises themselves. Webb looks far and finds the early universe arriving too quickly. It looks near and finds familiar worlds behaving in unfamiliar ways. It reads atmospheres, uncovers silent galaxies, follows active black holes into deep time, and then keeps moving, shifting scale without losing intensity. By this stage it becomes harder to think of the telescope as a machine designed for one realm alone. It does not belong only to the ancient universe, or only to planetary science, or only to the search for life. It is becoming something broader and more unsettling than that, a tool that keeps revealing the same underlying truth across every scale it touches. The cosmos is not merely richer than expected, it is less finished, less simple, and less willing to stay inside old categories. That truth becomes especially clear when Webb turns again to the frontier of distance and begins identifying still more remote galaxies, objects whose light has travelled from so early in cosmic history that the numbers alone begin to sound unreal. One of the most striking examples is the galaxy candidate later described as MOMZ14, a compact source whose measured redshift places it among the most distant galaxies ever identified. If that estimate holds, then the light now entering human instruments left when the universe is only around 280 million years old, less than a small fraction of its current age. The significance of such an object is not just that it extends a record. Records in astronomy matter, but mostly because of what they force into view. A galaxy that far away is a galaxy from an age when everything should still be close to the beginning, when structure is expected to be minimal and the first substantial system should still be rare. Yet here again, Webb does not uncover a weak, indecisive signal from a universe barely beginning to form. It finds a source bright enough to command attention, active enough to imply vigorous star formation, and real enough to deepen the now familiar discomfort. The record keeps moving backward, and every time it does, the universe refuses to look younger in the simple way it is supposed to. The early cosmos does not become emptier as Webb pushes toward it. It becomes more populated, more luminous, and in some cases more structurally convincing. The horizon recedes, but the mystery only thickens. That is where distance starts to lose its old emotional meaning. There was a time when the farthest observable galaxies were treated almost like the final edge of knowledge, too faint and too compromised for anything but rough inference. Now the edge is still there, but it is crowded with specific objects, each one forcing astronomers to say more than they expected they would ever be able to say. A compact star-forming galaxy, existing only a few 100 million years after the Big Bang, is not simply one more point in a chart. It is evidence that the universe may have built its visible complexity almost immediately, that the separation between primordial darkness and structured cosmic life is narrower than once imagined. Webb keeps taking what should be transitional time and turning it into active time. It keeps taking what should be a faint beginning and revealing something closer to a surge. Then, in a different register entirely, the telescope captures a collision that seems almost too symbolic to be real. Two galaxies appear intertwined in such a way that processed images evoke the shape of an infinity sign, a twisting figure of light and gravity that quickly becomes known as the Infinity Galaxy. It is visually striking, almost suspiciously so, and there is always a danger in astronomy that beautiful forms distract from the physics beneath them. But in this case, the deeper story is more important than the outline. Webb is not merely looking at a pleasing shape in space. It is catching two galaxies mid-merger, their structures distorted, their gas compressed, their gravitational fields tangled together in a process known to drive some of the most transformative episodes in galactic history. At the heart of that disturbance lies a feeding, supermassive black hole, a central engine drawing in matter amid the chaos. The image becomes memorable because it looks symbolic. It becomes scientifically potent because it is not symbolic at all. It is an actual case of violent galactic interaction, revealing how collisions can channel gas inward, intensify growth, and perhaps help explain how the universe's largest black holes acquire mass so effectively. This matters because the black hole problem is never far from the surface of Webb's discoveries. Earlier sections of cosmic history reveal black holes that seem too early. Later collisions reveal environments in which black holes can grow with savage efficiency. The Infinity Galaxy does not solve the origin of the earliest black holes, but it provides a vivid laboratory for understanding one route by which black holes and galaxies reshape one another over time. A merger is not just a crash of stars, since stars mostly pass without direct impact. It is a collision of gravitational systems, of gas flows, of tidal distortions, of dense clouds forced into new arrangements. Such conditions can drive furious star formation in one region and funnel material into the galactic nucleus in another. If the universe needs ways to accelerate black hole growth, mergers offer one of the clearest pathways. What Webb shows in this case is not only the beauty of a rare geometry, but the mechanics of cosmic appetite. The same universe that seems to grow black holes too quickly in its youth also reveals, at later epochs, the kinds of dynamic structures that can fatten those black holes through concentrated infall. Everywhere the telescope looks, gravity appears not as a calm organizer, but as a pressure that drives matter inward, compacts it, and turns order into heat. At nearly the opposite end of scale, Webb also produces one of the clearest early moments in the direct imaging of an exoplanet. HIP 65426b is not the first exoplanet ever directly imaged by human instruments in a broad historical sense. But Webb's observation marks a new threshold in how clearly such a world can be treated as an object with its own emitted light, rather than merely a side effect in the glare of a host star. This planet is large, young, and hot, a gas giant orbiting far enough from its star that Webb's coronagraph can suppress the starlight and isolate the planet's infrared glow. That distinction is important. Most exoplanet knowledge comes from indirect methods. The planet passes in front of the star, or pulls on it, or reveals itself by what it subtracts. Here the telescope captures the planet's own light more cleanly, giving astronomy access to atmospheric structure, cloud behavior, and composition in a different mode. Methane becomes relevant. Water vapor becomes relevant. Layered cloud systems become something more than speculation. For the first time at this level of detail, a distant giant world begins to look less like a calculation and more like a place with depth in its atmosphere and thermal character of its own. This, too, fits the larger pattern. Webb keeps turning abstractions into environments. A planet once known mainly by mass and orbit becomes a luminous atmospheric object with identifiable chemistry. A deep field once known as a patch of darkness becomes a crowded landscape of early galaxies. A cold moon becomes a venting ocean world. A distant planet like K218b becomes a chemically ambiguous arena where life is at least discussable in scientific terms. The telescope is not adding beauty to the cosmos, it is adding consequences. Once a world can be studied in this kind of detail, it becomes harder to talk about exoplanets generically. Every measured atmosphere, every directly imaged cloud deck, every thermal signature forces a shift away from categories and toward individual histories. And once that happens often enough, the galaxy begins to look less like a field of repeating planetary types and more like a library of singular worlds, each with its own conditions, its own chemistry, and its own hidden surprises. Even small bodies moving through the solar system do not escape this broadening of consequence. An object such as asteroid 2024 YR4 might never have become a public symbol in the way distant galaxies or potentially habitable planets do. Yet Webb's ability to observe such a body matters for a different reason. Small asteroids are difficult targets. They are faint, sometimes dark, often fast, and easily reduced to uncertain points of reflected light. Infrared observation changes that by revealing thermal behavior, surface composition, and size estimates with more confidence than visible brightness alone can provide. Such work may sound modest beside the drama of ancient galaxies, but in truth it belongs to the same story. A telescope capable of reading the earliest epochs of the universe can also refine understanding of a nearby object whose motion and physical nature matter for planetary defense, solar system history, and the broader physics of minor bodies. It means the instrument is not trapped by its grandest purpose. It can descend from the edge of cosmic time to a moving rock and still produce something valuable. That flexibility is part of what makes Webb so disruptive. It does not merely do one impossible thing. It does many precise things across wildly different scales, and the accumulation of those abilities begins to alter what astronomy expects a single observatory can be. Seen together, these observations form a kind of mosaic. The farthest galaxies keep pushing backward toward the opening moments of structure. Colliding systems reveal how matter and black holes can evolve through violence. Direct imaging of exoplanets brings distant worlds into a sharper physical reality. Nearby asteroids become measurable in ways that improve both caution and understanding. None of these belongs naturally in the same emotional category, and yet Webb ties them together by revealing the same habit everywhere. Whenever the telescope is pointed at something that once seemed adequately described in broad terms, the description starts to fail. Early galaxies are not merely early, they're unexpectedly alive. Galactic mergers are not just messy interactions. They're channels of concentrated growth. Exoplanets are not just detected. They're atmospheres, climates, heat signatures, and layered clouds. Asteroids are not just rocks on trajectories. They are thermal objects with histories written into how they absorb and emit light. This is why the sense of disturbance around Webb's discoveries cannot be located in one headline alone. It does not come only from record-breaking distance or from a potential biosignature or from a visually spectacular merger. It comes from repetition, again and again, in one domain after another. Clarity reveals that prior understanding has been thinner than it seemed. The telescope keeps showing that the universe is hardest to interpret precisely where it becomes easiest to see. The better the view, the stranger the implications. That is an unusual kind of scientific progress. Often better instruments resolve ambiguity and replace mystery with mechanism. Webb does that sometimes, but just as often it resolves ambiguity only enough to expose a deeper layer of uncertainty. A strange galaxy becomes a stranger population. A promising planet becomes a more complicated atmosphere. A beautiful collision becomes a black hole growth engine. A nearby asteroid becomes part of a larger web of dynamic solar system processes. Everywhere there is more specificity. And everywhere specificity seems to widen rather than close the interpretive gap. By now, the telescope's real subject is no longer just any single object it observes. Its real subject is the inadequacy of simplification itself. The universe will not remain a set of neat divisions between near and far, primitive and mature, active and quiet, lifeless and living, local and cosmic. Webb keeps crossing those divisions and showing that the boundaries are softer than expected. A distant galaxy can look mature. A young planet can carry atmospheric complexity beyond easy analogy. A small body can matter to the same observatory that studies the first stars. A merger half a universe away can illuminate processes that help explain the earliest black holes. The scales differ, but the message remains steady. No level of the cosmos is empty of hidden structure. No category is safe from revision once the light becomes sharp enough. That realization prepares the ground for the final shift in the story, because after enough discoveries of this kind, the telescope itself begins to feel less like a machine gathering answers and more like an instrument that changes the questions. It is not simply finding unexpected things. It is teaching astronomy that expectation has often been the weaker force. The universe, when finally examined with this much care, does not settle down. It grows more layered, more active, more difficult to summarize. Every record it breaks, every atmosphere it reads, every collision it clarifies, every moving object it tracks leads back to the same uneasy conclusion. The old map was never exactly wrong. It was just too thin for what was really there. By the time these discoveries begin to settle into the scientific record, something more subtle has already changed. The telescope is no longer just adding findings to astronomy. It is changing the mental habits behind astronomy itself. That may be the most disruptive effect of all, because facts can be absorbed one by one, reclassified, debated, and eventually folded into revised models. A shift in habit is harder to contain. Before Webb, Many of the biggest questions in cosmology and planetary science are framed within a certain emotional range. The early universe is assumed to be dim, sparse, and gradual. Exoplanets are treated as detectable but mostly inaccessible, more census than geography. Black hole formation is mysterious but usually discussed as a problem of slow accumulation. The solar system is regarded as rich but broadly mapped, full of details still to be learned but not expected to overturn its major narrative. Webb does not destroy those frameworks. It does something more unsettling. It keeps exposing the places where the frameworks become too comfortable. It reveals how often the old questions were built around assumptions of restraint, and how often nature seems to prefer excess instead. That is why the telescope's effect cannot be measured only in published papers or record announcements. Its deeper effect is that it narrows the distance between speculation and evidence, not by proving the wildest ideas correct, but by making some of them no longer seem absurd to ask. Could galaxies assemble with impossible speed under early conditions? Could some black holes be born already massive? Could parts of the universe preserve subtle asymmetries from deep origin conditions? Could a distant atmosphere contain chemistry that biology might plausibly help maintain? Could moons and minor bodies in the solar system still be dynamically active in ways that change how scientists think about habitability and chemical evolution? These are not all equally likely. They do not all belong to the same level of confidence. Yet Webb has moved them from the outer edge of speculation toward the interior of scientific discussion. That is a powerful and destabilizing transition. Once a question becomes empirically reachable, it stops being safely philosophical. It becomes urgent. What makes this so unusual is the way it happens across disciplines at once: cosmology, galaxy evolution, black hole physics, planetary atmospheres, solar system science, and astrobiology are often treated as neighbouring but separate territories, each with its own methods, instruments, and internal debates. Webb keeps cutting across those boundaries. An observation meant to study the first galaxies complicates black hole timelines. A planetary atmosphere observation changes the logic of biosignature searches. An image of a moon or comet alters ideas about where active chemistry persists close to home. A lensed supernova enters the argument over the expansion of the universe. The telescope becomes a bridge not because it was designed to unify every field, but because its sensitivity and wavelength coverage keep touching the pressure points of many fields at once. And once those pressure points are touched, the old compartmentalization starts to weaken. The early universe is no longer only about cosmology. It becomes linked to the origin of black holes, the timing of chemical enrichment, the first conditions for planet formation, and the broad question of how fast complexity begins. Likewise, the study of exoplanets is no longer only about counting distant worlds. It becomes entangled with atmospheric chemistry, climate, planetary formation, and the criteria by which life itself might someday be inferred from light alone. That widening has consequences for how evidence is now read. In earlier eras of astronomy, a single extraordinary observation could be greeted either as a sensational outlier or as a likely mistake. Webb has already produced enough unusual but credible results that the reflex to dismiss becomes harder to maintain. Not because caution has become less necessary, but because surprise is no longer rare enough to feel exceptional. Surprise has become patterned. The telescope keeps finding systems that occupy the narrow space between impossible and undeniable. That space is where science is forced to mature quickly. It cannot simply celebrate or reject. It has to refine, compare, reobserve, and rethink. The early luminous galaxies might eventually fit into new formation models, but only after those models have been pushed well beyond their previous comfort. The possible biosignatures on K218b may fade or strengthen, But either outcome will require a far more sophisticated understanding of non-biological atmospheres than existed before Webb. Early quiescent galaxies may turn out to be more common or less common than initial results suggest, but their very existence has already stretched the assumed pace of cosmic development. In every case, the telescope is not merely supplying data, it is raising the price of simplification. That matters because simplification has always been both the strength and the weakness of theoretical science. Models must compress reality, or they become unreadable. They have to identify the forces that matter most and let the lesser details average away. Most of the time, that works well enough. But every so often a new instrument reveals that what has been averaged away is not minor at all. It is structural. Webb has the feeling of one of those instruments. It keeps showing that the universe has more modes of behavior than the cleaner models assumed. Galaxies do not merely grow slowly and steadily. They can flare, compact, feed black holes, and fall partly silent with startling speed. Atmospheres do not merely advertise obvious chemistry. They mix signals in ways that can imitate, conceal, or complicate the search for life. Small bodies are not merely leftovers. They are chemical and dynamical records still changing under present conditions. Even cosmic time itself, when viewed through lensing and extreme distance, begins to feel less like a simple sequence and more like a layered archive where beginnings overlap with maturities and echoes arrive late. In that sense, Webb has altered astronomy's relationship to uncertainty. Older uncertainty often came from not seeing enough. A distant galaxy was too faint, a planet was too small, a spectrum was too noisy. The unknown sat behind a veil of limited data. Webb removes part of that veil. But the unknown does not recede in a neat line, it changes character. The new uncertainty comes from seeing enough to recognize that the old categories are incomplete. This is a harder kind of uncertainty to live with because it cannot be solved merely by turning up the sensitivity once more. It requires conceptual adaptation. It asks whether the timelines are wrong in detail, whether feedback acts earlier than assumed, whether the first stellar populations differ more radically than expected, whether black hole seeding takes more than one path, whether certain atmospheric molecules can no longer be discussed without a full planetary context, whether even the broad symmetry of the universe should remain a tested principle rather than an unquestioned background condition. These are not technical adjustments at the margins. They are revisions to the questions by which evidence is organized. And yet the telescope remains young in another sense. Many of its most significant surveys are still incomplete. Large observing programs continue to gather light from deep fields, transiting planets, dense star-forming regions, icy outer bodies, merging galaxies, and gravitational lenses. More spectroscopic confirmations are coming. More candidate galaxies at extreme redshift will be tested. More atmospheres will be compared. More local objects will be examined with a precision that earlier generations of astronomers could only imagine. The archive is expanding faster than interpretation can comfortably keep pace. That imbalance is itself revealing. For a long time, the shortage in astronomy is observational power. Now, at least in some domains, the shortage begins to feel interpretive. There is enough good data to challenge established pictures faster than the community can fully reorganize them. That is a sign not of confusion alone, but of transition. The telescope has moved the field into an era where discovery is no longer occasional confirmation of long-preferred ideas. It is a steady confrontation with a universe that keeps exceeding the emotional modesty of the models built to describe it. Perhaps that is why the most disturbing thing Webb reveals is not any one object, not the bright early galaxies, not the feeding black holes, not the silent early systems, not the atmosphere of K218b, not the lensed supernova or the collision shaped like infinity. It is the cumulative suggestion that the universe may be less patient than human theory expected. Complexity appears early, structure rises fast, chemistry becomes interesting quickly. Worlds begin to look individual the moment they are studied properly. Hidden oceans leak. Ancient light arrives warped but legible. Small objects close to Earth turn out to hold important detail, while immense structures at the edge of the visible universe turn out to feel crowded and oddly mature. Everywhere the same impression returns. The cosmos does not wait for understanding to catch up before it becomes intricate, and that leaves astronomy in an unusual position. It has never had more power to observe, and yet observation is producing a deeper style of unease. The old confidence that better data would mostly confirm the broad story has given way to something less stable and more alive. Better data still confirms much, but it also keeps uncovering awkward timings, accelerated pathways, conflicting interpretations, and conditions that do not fit neatly inside the developmental stages once assumed to govern the universe. It is not a collapse of knowledge. It is something more interesting, a widening of what counts as possible. A growing suspicion that the tidy version of cosmic history may have been shaped as much by observational limits as by nature itself. So the telescope continues to look, and the deeper it looks, the more its function seems to change. It is no longer simply a witness to the universe. It is becoming the instrument by which the universe resists being summarized. Every observation sharpens reality, and reality keeps refusing to become smaller. The first galaxies remain too luminous in memory. The first black holes remain too hungry. The first quiet galaxies remain too old for their age. The strange chemistry in distant skies remains unresolved. The near objects remain unexpectedly active. The grand structure of the cosmos remains impressively coherent, and yet dotted with just enough stress points to keep every broad conclusion slightly unsettled. If this is only the beginning of what such an observatory can uncover, then the real disturbance may not lie in any current anomaly at all. It may lie in the possibility that the universe has only just begun to show how much of its history has been happening faster, earlier, stranger, and with more hidden continuity than anyone was prepared to see. The deeper James Webb looks, the less the universe resembles a story that unfolds in clean stages. It begins to look like something already in motion long before anyone expected it to be. In the space of only a few years, ancient galaxies have appeared brighter and more mature than they should. Black holes have emerged already feeding in epochs once thought too young to support them. Some galaxies seem to burn through their youth and fall quiet almost as soon as they arrive. Distant planets, once known only as passing shadows, now reveal atmospheres full of chemistry that is real enough to measure and strange enough to resist easy explanation. Even nearby worlds and smaller bodies, long treated as familiar, continue to show signs that they are more active, more layered, and more unfinished than they first appeared. None of this proves that the universe is broken. It does something subtler than that. It suggests that the old picture may have been too smooth, too patient, too certain about how quickly matter becomes structure and how quickly structure becomes mystery. Webb does not replace darkness with perfect understanding. It replaces vague darkness with sharper uncertainty. And that may be the more important gift. It means the unknown is no longer somewhere beyond reach. It is here, inside the data, inside the timelines, inside the atmospheres and galaxies and distant flashes of bent light that still refuse to settle into one final meaning. So the telescope keeps watching. More observations are waiting. More deep fields remain to be opened. More atmospheres will be read. More ancient systems will come forward from the dark. And somewhere in those measurements, perhaps hidden in another impossible galaxy or another strange planetary sky, there may be an answer, or perhaps only a better question, quieter and deeper than the last.